This is a tutorial on the properties of functions. The first thing that we're going to talk about in this tutorial is determining whether our function is increasing, decreasing, or is a constant function. Now we're given three different graphs, and this first graph is the graph of an increasing function. If I started at negative infinity on the x-axis and I walked along the x-axis towards positive infinity, and as I walked along this axis I recorded my y value or my function value. If, as I walk along the x-axis, my y value gets larger, then you have an increasing function. In our second graph, the opposite is happening. This is a decreasing function. As I walk along the x-axis, my y values are getting smaller, or their value is decreasing. So as x gets bigger, y gets smaller. If that's what's happening, then you have a decreasing function. Now in our last graph, here our function is constant. As I walk along the x-axis, my y value does not change. It stays here at 3. Since my y value doesn't change as x gets larger, that means I have a constant function. Now let's look at this graph of this squiggly line. From here to here, our function is increasing because our y values are getting larger as x gets larger. But between these two segments here, our function is decreasing because our y value is getting smaller as x gets larger. But then after that, our function goes back to being an increasing function because here our y values are getting larger until we hit this point here where again our function becomes a decreasing function because our y values are getting smaller. And then finally we come to this final point where now our function becomes an increasing function again because our y values or our function values are getting larger as x gets larger. These points where our function switches from being an increasing function to a decreasing function and then back again to an increasing function, these points are called local minimum and local maximum. This first point here is not the largest point on the graph, or this point does not have the largest y value on the graph. But between this range and this range, this point has the largest y value. It's not the largest y value for the whole function, but locally, or close to it, all these points have smaller y values. So this is a local maximum. Here at our fourth point here, this is what we call a local minimum. It is not the smallest or the lowest y value on our graph, but in the range of points near it, it is the smallest y value or has the smallest function value. So this is a local minimum. These local maximums and local minimums occur when our function goes from being an increasing to a decreasing function, or a local minimum occurs when our function goes from being a decreasing function to an increasing function. Again, these are not the maximum or minimum spots on the function, they're just the local minimum or the local maximum. Now the next thing we need to talk about is the average rate of change of a function. Now because a lot of functions are not straight lines, they tend to be these bent lines, if we want to find the rate of change, we typically find the average rate of change between 2 points. Say I wanted the average rate of change of this function between the points 3, 3 and 11, 11. Well, then I could approximate the rate of change of this function by finding the rate of change of the line between these 2 points. Now remember, the rate of change of a line is just the slope. So the average rate of change of this function, which I'm approximating with this line, is just the slope of this line. My change in y, or the change in my function values, well, that's 11 minus 3. And the change in x, again, is 11 minus 3. So this is 8 over 8, which reduces to 1. So the average rate of change of this function between these 2 points is 1. This function, on average, goes up 1 in the y every time it goes 1 in the x. Now you'll notice that the average rate of change of a function changes depending on where you pick the points. Say instead I picked the point 7,5. And I wanted to know the average rate of change of our function between 7 and 11, where x is 7 and x is 11. Then I would approximate it with this line, and then my change in y becomes 11 minus 5, and my change in x is 11 minus 7. This is 6 over 4, or 3/2. So notice I have a different average rate of change when I pick 2 different points on my function. So if you're ever asked for the average rate of change of a function, you have to be given an interval, or 2 x values, to be able to find the average rate of change. Now let's say you were asked for the average rate of change of a function, but you weren't given the graph. Remember that the average rate of change is just the change of y over the change in x. Now, b and a here in this formula is just the different x values. Before, you could say that these were 11 and 11. Or 11 and 7, depending on which of the 2 previous points I had used before. Now the function, when x is equal to b, this is just the y value at that x value, b. And the function value at a, this is just the y value again, but it's the y value when x is equal to a. This is the exact same equation as the slope equation. y2 minus y1 over x2 minus x1. But instead of y2 and y1, we're using function notation, so it's the function value at b minus the function value at a. So if I wanted to find the average rate of change for this function, f of x is equal to 3x squared minus 4x, where x ranges from 0 to 2, that just means that 0 is a and 2 is b. And then I'm going to use my formula where the change in y over the change in x is equal to the function value when x is b minus the function value when x is a over b minus a. Well, I already know b and a, 2 and 0. Now I need to find the function values when x is 2 and 0. So if x is equal to 0, then my function value, that's equal to 3 times 0 squared minus 4 times 0. I'm just plugging in 0 for x, and this is equal to 0. Which means if I plugged in 0 for x and a was 0, that means the function value at a is equal to 0. Do the same thing for b, or when x is equal to 2. So the function value when x is equal to 2 is equal to 3 times 2 squared minus 4 times 2. All I did was plug in 2 for x. 2 squared is 4, 4 times 3 is 12. 4 times 2 is 8, so 12 minus 8, that's equal to 4. So our function value when x is equal to 2 is 4. But remember, 2, that's b. So our function value when x is b is equal to 4. So I have everything I need. I'm going to plug in this for that, this for that. A is going to be 0 and b is going to be 2. So my average rate of change for this function between these 2 points, that's equal to 4 minus 0 over 2 minus 0, which is equal to 4 over 2, or it's equal to 2. So the average rate of change for 3x squared minus 4x over the interval from 0 to 2 is just 2. It goes up 2y for every 1x, and that's an approximation. Now when we find the average rate of change of a function, we're picking 2 points. Say this point here, 11, 9. And this point here, 2, 3. And we approximate the average rate of change between these 2 points by finding the slope of the line between these 2 points. Well, this line that we're finding the slope of, this is called the secant line. And sometimes we're asked to find the equation of this secant line. The first thing that we're going to do is find the average rate of change between these 2 points, because that'll give us the slope of this line. So our change in function value, or the change in our y value, that's 9 minus 3. And then the change in our x value is 11 minus 2. So this is 6 over 9, or 2/3. So the slope of this secant line is 2/3. Now if you want to find the equation for this secant line, use standard slope-intercept form, where m is our slope and b is our y-intercept. And we know our slope, that's 2/3. So what we do is plug that in for m, and then pick either of these points, because we know these points are on our line, and plug them in for x and y. Then we'll be able to find the value of our y-intercept. So I'm going to pick the point 2, 3. I'm going to plug 3 in for y. I'm going to plug in our slope of 2/3. And then I'm going to plug in our x value of 2 and solve for b. So we have 3 is equal to 4/3 plus b. Subtract 4/3 from both sides. And we'll get b is equal to 1 2/3. So the equation of our secant line is y is equal to 2/3 x plus 1 2/3. Now the last property of functions that we have to talk about is determining whether a function is even or odd. When we say a function is even or odd, we're saying something about the graph of that function. An even function is symmetrical to the y-axis. An odd function is symmetrical to the origin. Now, not all functions are even or odd. Some functions are neither even or odd. If you want to determine if a function is even, well, then you have to look at the graph and see, because an even function is symmetrical to the y-axis. If you have the equation of a function and you want to determine if it's even, well then the function for any negative x value has to give you the same value as the positive x value. Now, if you have an odd function, odd functions are symmetrical to the origin. But if you don't have the graph of the function, you just have the equation, well then negative values of x should get you the same function value, but the function value should be negative. So let's look at some examples. Here I have three equations. My first one, f of x is equal to the absolute value of x. Well, if I suspect that this function is either even or odd, I have to remember that if it's even, my function value of negative x is always equal to the function value of x. And if it's odd, then the function value of negative x has to give us the negative function value. If I plug in negative x into this function, then the function of negative x is equal to the absolute value of negative x. And since this negative is inside the absolute value, it just goes away. So the function value of negative x is equal to the absolute value of x, which is exactly what our function is. So this first statement is true. And this statement is true for all even functions. And that means f of x is equal to the absolute value of x is an even function. Now let's look at the second one. Here we have g of x is equal to x cubed plus 2x squared plus 3x plus 4. So I'm going to find g of negative x. So if I plug in negative x, 4x in all of these terms, I'll have negative x cubed plus 2 times negative x squared plus 3 times negative x plus 4. Now negative x cubed is just negative x cubed. Negative x squared is a positive x, so plus 2x squared. 3 times negative x would be minus 3x, and then plus 4. So our function for negative x is equal to negative x cubed plus 2x squared minus 3x plus 4. All we did was switch the signs of the first and third term, but not the second or fourth term. So this equation is not f of x, and this equation is not negative f of x, because only two of the terms went negative. So this is not an even or an odd function. This function is neither. Now let's look at our last function, h of x. That's equal to x cubed minus x, so if I plug in negative x here, h of negative x is equal to negative x cubed minus negative x. This will simplify into negative x cubed plus x. Now if I factor a negative 1 out of here, this will be negative 1 times x cubed minus x. This is h of x. So what I have here is negative 1 times h of x, or the negative of our function value. So since this one satisfies our second condition here, this is an odd function. Now if we're given the graph of a function, it's very easy to determine whether it's an even or an odd function. Remember, even functions are symmetrical across the y-axis, and odd ones are symmetrical across the origin. If I go to my first graph here, this parabola, if I have the point 4, 0, and this is symmetrical across the origin, I should have a point at negative 4, 0, which I do. If I have the point 6, 7, then if I'm symmetrical across the origin, I should have a point at -6, -7, which I don't. So this cannot be odd. If it's even, then I should be symmetrical across the y-axis. So this point is a distance of 6 from the y-axis, and if I go 6 the other direction from the y-axis, I should run into my graph, which I do. I can see that this parabola is symmetrical across the y-axis. So I would say that this is an even function. Our second graph here is not symmetrical across the y-axis. But if I have the point 2, 2, and I'm symmetrical across the origin, I should have the point -2, -2, which I do. In fact, all of these points are symmetrical across the origin. So I would say that this second graph is an odd function. Now my last graph is not symmetrical across either the y-axis or the origin. It does not mirror across the y-axis. And it does not mirror across this point, the origin. So I would say that this function is neither. So that's how you identify even and odd functions using their graphs. And that completes the tutorial on properties of functions.